You know, when we talk about Taiwan's energy future, it always feels like we're stuck in the same endless debate. It's this constant tug-of-war between two very familiar options. But what if there's a third path? A completely new scientific approach that could change the entire conversation. Okay, let's dive into this.
For years, it's been framed as this impossible choice. On one side, you've got the incredible power of nuclear energy, and on the other, you have the clean promise of renewables. But the thing is, for an island facing some pretty unique pressures, neither of these has turned out to be a perfect solution. And that's created what a lot of people see as a political and national security deadlock.
Let's just quickly break down this dilemma, right? With nuclear power, the social concerns are huge. Taiwan is in a seismic zone, so the fear of a Fukushima-level disaster is very real. And then there's the problem of what to do with high-level nuclear waste, a challenge that we still haven't solved. But then when you look at renewables like wind and solar, you run into different problems. They're not always on, and the amount of land they need makes it incredibly hard to generate the kind of stable, 24/7 power that Taiwan's world-leading AI and semiconductor industries absolutely need.
So, in this explainer, we're going to map out a potential way out of this whole mess. First, we'll dig into the high stakes of Taiwan's current energy situation. Then, we'll introduce this third path, a technology called ICS-TEC. We'll get into the science of how it works, tackle some of the doubts you might have, and even see if it could realistically replace a nuclear power plant. And finally, we'll look at how this could shift the entire debate for good.
Okay, let's start with the deadlock itself. And this isn't just some abstract problem, it's a really pressing issue, driven by a huge spike in demand and some very serious national security risks.
The pressure is really coming from all sides. You've got this explosive growth in AI and advanced chip making that just eats up electricity. At the same time, Taiwan's trying to hit its 2050 net zero emissions goals. On top of all that, a staggering 98% of its energy is imported, which makes the island incredibly vulnerable. And think about this. In a conflict, big centralized power plants like nuclear facilities become obvious targets. So finding a resilient, domestic, clean energy source isn't just a nice idea, it's a matter of national survival.
And that brings us to this potential third path. It's a technology called IC-TEC, which stands for Ion Centrifugal Thermal to Electric Conversion. It's a completely different way of thinking about how we generate power.
So what is it exactly? Well, at its core, IC-TEC is a way to take the disorganized, chaotic heat energy that's just all around us, in the air, in the ground, and turn it directly into electricity. And the way it does this is by using an acceleration field, think of the pull of gravity or the force inside a spinning centrifuge, to sort charged particles, or ions, by how much they weigh.
Now, I know this might sound a little like science fiction, so let's break down the actual science behind it. How do you go from messy, chaotic heat to organized, usable electricity?
Okay, it's basically a four-step process. Picture a liquid with positive and negative ions just floating around in it. First, you apply an acceleration field. Just like how gravity pulls heavier air molecules down, this force makes the heavier positive ions sink and the lighter negative ions rise. Simple enough. This separation of charges creates a stable internal electric field. You've got yourself a voltage. And here's the really cool part. Step 4. The constant random jiggling of all those ions from the ambient heat around them is always pushing them against this electric field. It's like it's constantly recharging the system. That's how the chaotic energy of heat gets turned into a directed electrical current.
And the key scientific insight here is this. The amount of voltage you get only depends on two things: the difference in mass between the ions and how strong the acceleration is. It doesn't matter how much stuff you have in the solution. This actually explains experimental results that a physicist named R.C. Tolman saw all the way back in 1910. So this modern theory has some deep historical roots.
Now, whenever a new energy technology comes along that sounds this revolutionary, you should be skeptical. It's not only natural, it's necessary. So let's just tackle the tough questions head on.
The first and most common question is usually about the models that use a centrifuge. If the machine is spinning, isn't the energy just coming from the motor that's making it spin?
And the answer to that is a definitive no, and it's all grounded in some pretty basic physics. Think about it this way. If you built a static IC-TEC device, no spinning parts, and just set it on the ground, if it drew power from rotation, it would have to be stealing that energy from the Earth's spin, which would actually cause our planet to slow down. That would violate the law of conservation of angular momentum, which is, well, impossible. The energy source has nothing to do with the mechanical rotation itself.
Okay, so if it's not from the spinning, then what is this? Is it some kind of perpetual motion machine in disguise? If it just runs and runs, where's the fuel coming from?
The fuel is the heat that's already in the environment all around it. See, this isn't a closed system trying to create energy from nothing. It's an open system that's harvesting thermal energy that's already there. The acceleration field just acts like a gatekeeper, kind of like the famous Maxwell's demon idea from physics, that sorts particles without doing any work itself. It just turns that random, chaotic vibration of heat into an organized flow of electricity.
And we know this is a continuous process, not just some temporary chemical reaction. How? Well, get this. Experiments have run for over 700 days, producing a stable, continuous electrical output. If this were just some simple diffusion effect, it would have fizzled out in about 12 to 36 hours. The fact that it just keeps going proves that it's constantly converting environmental heat into new electrical energy.
So the science seems to check out. But can it scale? Can it actually work in the real world? Let's get practical and look at what it would take to replace Taiwan's controversial fourth nuclear power plant.
Okay, so based on calculations using materials that already exist, like high-strength aluminum alloy, an IC-Tech system could generate about 72 watts per cubic meter. But here's the real key to making it scalable. The physics says the power output is proportional to the rotational speed to the fourth power. That means if you double the speed, you don't just double the power, you increase it by a factor of 16. That's a massive potential for engineering.
So how does it actually stack up against nuclear? Well, for safety, IC-Tech has zero risk of a meltdown or radiation leak. Waste? There's no nuclear waste to worry about. Carbon emissions? Zero. Land use is tiny, since you can build these things underground, which means no giant safety zones. And for national security, because you can build lots of smaller, decentralized units, it's way more resilient than having one single massive target like a nuclear plant.
And all of this brings us to the big picture. This technology, ICETC, it really offers a chance to reframe the whole energy conversation, to move it away from politics and toward a new scientific path for Taiwan.
The promise here is just so powerful and clear. It's a third path for Taiwan's energy future that offers a no carbon, no radiation, no waste solution. It just completely sidesteps the biggest problems of both nuclear power and renewables.
And look, this isn't happening in a bubble. To make sure the science is solid, the core theory was sent out as a formal challenge to over 6,000 professors at universities all over the world. And as of today, not a single one has been able to find a flaw in the theory.
So at the end of the day, this debate doesn't have to be a stuck binary choice between two imperfect options. This is really a call for everyone, on all sides of the argument, to look past the old talking points and consider a genuine third way, one that's based on science. And it leaves us with this one incredible question. Could a physical effect, first spotted in a forgotten experiment way back in 1910, really hold the key to rewriting Taiwan's entire energy future?